Okay, so welcome everyone for today's DMAP seminar. Today we have Stefan Felsner as our speaker. He's a professor at TU Berlin already for many years, and he's a well-known expert in discrete geometry, also in partially ordered sets, and also in many aspects of graph theory, such as graphs with geometric representations and also graph drawing. And today he will talk about combinatorics of pseudocircle arrangements. So please, Stefan.
Yeah, thank you, Thorsten. Thank you for the invitation. And so I'm going to share my my sheets of paper, and so I will disappear. Here is, I hope you can see it, my title slide, so to say. So it's about combinatorics of pseudocircle arrangement, and most of it is joint work with my postdoc, Scheucher, but some other people which are not on the title slide also contributed to parts of it. So let's start with the, well, let me say a word of motivation. So arrangements of line or arrangements of circles are things which are of some interest, and it was observed maybe by Goodman and Pollack, or maybe by others, that if you relax the notion, the geometric notion, and you move from lines to pseudo lines, being just curves which behave like lines in some respects, or if you go from circles to pseudocircles, then you are in a situation where you can in some way more clearly see the combinatorics and apply combinatorial arguments. So yeah. So this is what we are going to study, the combinatorics of pseudocircles. And pseudocircle is just a closed curve in the plane or on the sphere. Sometimes it's good not to have a specific outer face. And yeah, an arrangement of pseudocircles is a collection of such closed curves such that any two of them behave as circles would do. So they can be intersecting, or they can be touching, or they can be disjoint. These are the three relations that are possible. Now, an arrangement is simple if there is no crossing of at least three pseudocircles in one point, and we also forbid touchings in simple arrangements sometimes. And an arrangement is intersecting if any two pseudocircles intersect. And simple intersecting arrangements will be the key objects of our study. And to begin with, let's look at n equals 3. So we already saw what happened with n equals 2. Now let's go to n equals 3. And then we see that there are two ways for a simple arrangement on the sphere. Either you have the group arrangement or the non-group arrangement. And well, they are clearly distinct. Here every face is a triangle, and here in the center you have a face of degree 4, and you have also faces of degree 2. And yeah, so if you go on, then for n equals 4, there are 8 different intersecting arrangements. And if you continue, then for n equals 5, you have 278, and I won't read you these numbers for 6 and 7. It's known that the asymptotics of the number of different arrangements is 2 to the theta of n squared. And yeah, then you can relax the intersection property and only ask for the arrangement of being connected, and then you have some some more, or you can restrict and you talk about great circle arrangements or pseudo great circle arrangements, and you have a fewer. Yeah, and I already mentioned faces in an arrangement, so you just count the number of segments on the boundary that come from different pseudocircles. And yeah, since a simple arrangement is in some sense a four regular planar graph, then if you have n pseudocircles, it's easy to see that the number of faces is n squared minus n plus 2. And yeah, some special faces we are interested in are digons, or also called lenses. These are faces of degree 2, and triangles faces of degree 3. And now I have 3 different chapters. Somehow they come from different papers we've been working at this topic. The first is on the facial structure, triangles and digons. Then I have something about circularability, and the third one is colorings. And yeah, we'll see what time allows to see. So let's start with Grünbaum. Grünbaum in 72 wrote a nice little book, Arrangements and Spreads, and in this book he has a lot of conjectures. And one of the conjectures in this book is, if you have an arrangement of pseudocircles which is simple and intersecting and diagon free, then you have at least 2n-4 triangles. And yeah, in some sense, this is a relative of a result about triangles in arrangements of pseudolines, where the result is, if you take Euclidean pseudolines, then the result is you have at least n-2 triangles. And if you look at projective arrangements of pseudolines, then there is a classical paper from 1924 by Levy, who he showed that you have at least n triangles in this case. So this Greenbaum conjecture in some sense is generalizing this, and Greenbaum already came up with examples where this number is attained. And here you see a general construction, so you can do this blue structure with any number of lines. If you close it on the cylinder and put it back in the plane, you see that we are talking about pseudocircles. So any two of the guys intersect twice, and yeah, then you have these 3 extra pseudocircles which make it possible to have only 2n-4 triangles. So it's not completely trivial to find examples where you have so few triangles. Now, to see that we have some triangles, we can use the sweeping technique, which was for the situation of pseudocircles, was established by Snoeyink and Hershberger in '89. They show that in an intersecting arrangement, every pseudocircle has at least 2 sweepable cells on each side. And the sweepable cells in this context are triangles or digons. So if you have a digon-free arrangement, then every pseudocircle will have at least 4 incident triangles. And now a triangle contributes to 3 pseudocircles, so you have in total at least 4/3 times n triangles. And yeah, actually there exist arrangements with only 4/3n triangles. Here's an example with n equals 9 and only 12 triangles, but this is a non-simple arrangement. So here you have this point and this point, and these are points where multiple pseudocircles intersect. So again, some of the pseudocircles are closed and some are open. So you wrap them, you close them on the outside. So the simplicity is something important here. Yeah. So this is where we are now. We have seen the conjecture 2n-4 and a lower bound for thirds. And now the news, it's already a while since we found this, is that Greenbaum's conjecture is wrong. So here you have an example with 8 pseudocircles and only 11 triangles. So you would have 12 if Grünbaum's conjecture were true. And here's a larger example. Here's an example where we have n equals 12 and only 16 triangles. So this is actually the 4/3 n that is tied here. And what we did is we took this example, and from this example we produced a family, infinite family, where the ratio of triangles and where the number of triangles approaches 1.45n. And let me give you the idea of the construction. So the first observation is that our example admits a cut path. A cut path is a path which is cutting through each pseudocircle exactly once. So in another way of saying it, in some sense, the arrangement is a cylindrical arrangement. You could put it on a cylinder with everything wrapping around there. So we have this cut path, and we can cut it open along this path and stretch basically the cut, so that you have the small arrangement, and then the 12 pseudolines go parallel in this annulus. And now the idea is to pick one of the pseudocircles of the arrangement that we already constructed and replace it with this collection of 12 pseudocircle, and you fit this area where all the crossings are, you fit them in one of the triangles incident to the replaced line. And then you do a count, and you see that if you choose a cut path so that it destroys a triangle here, and then you get new triangles here on the boundary where you put this in, and yeah, so you see that you replace a number of pseudocircles by you replace one by 12, so you add 11 in each step, and the number of triangles you add 16 in each step. So if you iterate, you approach the 16/11 in the limits. So we were quite happy with this, but then later came up with a new replacement strategy, which is in some sense easier. So from the Hershberger-Snoeyink result, we know that we find 2 triangles on each side. So we have 4 incident triangles to the pseudocircle. And now we replace the green pseudocircle by a collection of 4 pseudocircles, so that all the crossings of these 4 pseudocircles are basically in these triangles. And yeah, then you increase the n by 3, and if you do the count, you have 4 up here, and then you have 8 triangles here, so you increase the number of triangles by 4, and this construction shows that the 4/3n that we got as a lower bound from the Snoeyink is actually the truth. Yeah, so this is the true value, and here's a new challenge. All the examples that we know contain which violate the Greenbaum conjecture, contain a specific arrangement where we know it is non-circularizable. So it has no representation with actual circles. So the question is, the new conjecture, if you have an arrangement of true circles, which is simple, intersecting, and Diagon free, then in this case, the Grünbaum conjecture is true. A proof of this would be quite nice, because in many cases you would have a proof of non-circularizability just by counting triangles. If you find an arrangement which has too few triangles, then you already know it's not circularizable. Yeah, and the support for the new conjecture is that this specific arrangement n delta 6, which is obtained from the group with a single step of the new replacement strategy. This has 6 pseudocircles and 8 triangles, and it is a sub-arrangement of all the examples we know. Okay, so that much about triangles. Let's switch to Diagons. And here is another conjecture of Grünbaum. He conjectures that if you have an arrangement of pseudocircles which is simple and intersecting, then the number of Diagons is upper bounded by 2n minus 2. You cannot have more. So here is an example, basically a sequence of circles and then 2 touching them on top and on bottom, and this here you have equality with this 2n minus 2. Yeah, and the conjecture is from 72, and then 30 years later, a collection of authors in a paper where they discuss lenses in arrangements of pseudocircles, they prove that this is true if the arrangement of pseudocircles is cylindrical. So if you can draw it on a cylinder so that every pseudocircle wraps around once. And in general, the number of Diagons or lenses is in O of n. This is what they could show, and I want to give the idea of the proof that they use. So since the arrangement is cylindrical, we can cut open the cylinder, and then we have a drawing like here. And now you see that if you have two pseudocircles which touch or which form a Diagon, if you have a Diagon, you can also make it a touching. So now we talk about touchings. If you have two and they touch, then yeah, one is the upper and the other is the lower. And if you look for the lower is the lower in every touching, because otherwise you would have this orange guy would separate two pseudocircles. They could not be intersecting anymore. So everybody is either from below or from above. And now this makes a two coloring of the pseudocircles. Here the upper four are from above. The three down here are from below. And now we make an edge when we have a touching. And now here comes something quite nice. Of course, this is a bipartite graph. This is what I already explained. And you have this. Then there is a drawing rule. So if you have an edge between two and somebody in between, you look at somebody in between. If its first exit is or touching is with the lower one, then you go on the right. If the first touching is with the upper one, you go to the left. And then it takes a case distinction to see that this drawing of the bipartite graph here on the boundary, this is going to be a Hanani-Tat drawing, meaning that two independent edges will have an even number of crossings. And the Hanani-Tat theorem tells us that if you have a Hanani-Tat drawing of a graph, then this graph is planar. So the result is that the touching graph of a cylindrical arrangement of pseudocircles is a bipartite planar graph. And we all know that bipartite planar graphs don't have too many edges. So yeah, they have at most 2n-4 edges. And from this, we get that the arrangement has at most 2n-2 lenses. The difference here comes from the fact that the two extremal faces can be lenses. Like here in this example, on the top, you only have two incident pseudocircles. And the same here on the bottom. So these are two lenses which are not counted in this bipartite graph, which are not touchings. Okay, this is this very nice result. And now then we've been looking at lens graphs in general, and yeah, it turns out they are not planar anymore. So here you have a K5 minor, for example. But yeah, but what we saw is that if they attain this 2n-2 number of edges, then they have a triangle. And actually, we can show that if the lens graph has a triangle, then there are not too many lenses. And so the lens graph, here is an example. And whenever you have a lens, here the vertices are the pseudocircles, and you make an edge when you have a lens. And here is the idea. So we have a triangle. We have a we have three pairwise touching pseudocircles. And now we focus on the interior triangle we can also do the same with the exterior because we are on the sphere. It's the same structure. And here is the internal situation. We can color the strings which come here. The green ones will be those which avoid the green side, so they run between the red and the blue side. These are green, and the red ones between the green and blue, and so on. And so we have a three coloring of these internal arcs. And what we can do is we can redraw the inner situation so that that you get essentially a point which separates the outer red from all the inner red, and the same with green and blue. And if you do this on the other side as well, then you see that you arrive at something which is almost cylindrical. The only obstruction against being cylindrical is that we still have the three pairwise touching circles. So the drawing is like this. You have the blue, the green, and the red, and they touch here. This is the triangle, and you have the other stuff. And now from this, we go to something which is truly cylindrical. We double the red guy and move it out to the far to the bottom or far to the top, depending of whether we take the lower or the upper arc from this pseudocircle. So we add three pseudocircles, but now we are in the situation that we have a cylindrical drawing. And now we can apply the argument from before, and with a bit of care, we can. So this situation of the touchings here can be made to something like this picture where you have two touchings, and then the new counts are you have three pseudocircles more, you have three touchings more. You know from the argument before that the number of touchings is at most 2 times the number of pseudocircles minus 5. So we can use the -4 bound from the bipartite planar graphs, because this time on the top and on the bottom we don't have a Diagon phase. And in addition, we can argue that the edge between the top and the bottom could be added. So it's not a quadrangulation. It misses at least one edge, and then from this we get that the number of touchings is at most 2n-2 in this situation. Yeah, and so the case that's remaining is that you have an arrangement which is intersecting, not cylindrical, and has no triangle in the length graph. And here we don't yet know how to prove that 2n-2 edges in the length graph is an upper bound. Yeah. Last slide for this part. Yet another conjecture of Grünbaum. He conjectured that the number of triangles again in an arrangement of pseudocircles which is simple and intersecting, but this time we don't have Diagon free. In this situation, the number of triangles should be at least n-1. And this is tight. Here is an example. Here you see many Diagons. And yeah, the lower bound again comes from the Hershberger-Snoeyink sweeping argument, and this time it is 2/3 n. So we know that we don't have the Hershberger's Snoeyink argument says on each side of a pseudocircle you have two sweepable things, and the sweepable things are triangles or digons. But if the arrangement is intersecting, you cannot have a digon or a touching from both sides, because then you would have two pseudocircles which are separated. So this is not possible, and so on one side you only have triangles, so you have two triangles with every pseudocircle, and this gives this bound. Okay, let's see. Maybe I continue with colorings, and we skip the circularizability. The starting point of the coloring thing is a conjecture from 98, which says that every simple great circle arrangement is 3 colorable. So it's very easy to see that every such arrangement is 4 colorable. There are 2 reasons for that. One is that it's 4 regular and not one of the Brooks examples. And another reason is that it's planar. So 4 colorability is for free, basically. And now the question is whether the 3 is true. And the conjecture has been looked at by some people, and basically no progress. So where does it come from? Well, if you have a line arrangement, then it's very easy to see that in the simple case you are 2 degenerate, so there's a 3 coloring. And you can also think of a sweep procedure which goes through the simple arrangement of lines or pseudo lines and does the job. If you're not simple, then the 3 colorability is not true anymore. Here, this Moser-Spindle can be realized by lines, and requires 4 colors. Now, there are also arrangement of circles which require 4 colors. So here is an example. It is still intersecting. We have 5 pseudocircles, and I claim that this arrangement requires 4 colors. So suppose it is 3 colorable. Then on this 4 face in the middle, there will be 1 color in a 3 coloring. There will be 1 color which is occupying 2 diagonally opposite vertices. And now this is not going to be red, but here we have a triangle, so one of these 2 guys will be red again. And by symmetry, we can pick any of the 2. And now let's see. On this triangle, these 2 points are already forbidden. They cannot be red, so this must be red. And now in this triangle, this has a red neighbor, this has a red neighbor, so this has to be red. And now in this triangle here, these 2 have each a red neighbor, so this must be red. And finally, in this triangle, these 2 have red neighbors, so this must be red. Yeah. So we have from the without of loss of generality assumption at the very beginning, we found a couple of red guys, And now if we look at the uncolored guys, then 1, 2, 3, 4, 5, 6, 7. We have a 7th cycle. And the 7th cycle, everybody here has a neighbor in red already. So we need 3 more colors to color the 7th cycle. Yeah. So it's really quite a tight conjecture. If you move away from the conditions of the great pseudocircle, where every triple is a group, then you already run into this kind of counterexamples. Yeah, so here's some data. These are intersecting arrangements with chromatic number 4. This is a different drawing of the guy that we just studied. But there's a second one with 5 pseudocircles, and then there's some with 6, and there's one with 7. And yeah, in all these examples, you see diamonds. So you see this kind of thing, a lens which is cut by one pseudocircle. And from these data, we have a new conjecture. Every diamond-free simple intersecting arrangement of at least 6 pseudocircles should be 3 colorable. This would, of course, imply the original conjecture. And even more, every sufficiently large simple intersecting arrangement of pseudocircles is 3 colorable. So it seems that the counterexamples are only on small numbers. For bigger numbers, it might be true that you always find 3 colorings. Now here's a remark: if you have a great circle arrangement, then you have an antipodal structure. You have the equator, and the inner and the outer are isomorphic, and then you can ask for an antipodal 3 coloring, so that the antipodal points get the same color. And this would an antipodal 3 coloring is a 3 coloring of the corresponding projective pseudoline arrangement. And yeah, here again we have looked at the small examples, and it turns out that all pseudo-great circle arrangements with n equals 7, 8, 9, 10, 11 have antipodal 3 colorings. Only these 2 guys with n equals 6, they don't have an antipodal 3 color. And clearly we conjecture that when you have a large great circle arrangement with n at least 7, then you have an antipodal 3 coloring. Yeah, so lots of conjectures. We are going to prove something, and we are going to prove something for triangle saturated arrangements. So a triangle saturated arrangement is an arrangement where in the 2 coloring of the faces. So we are talking about a 4 regular graph and planar graph. So the you have a 2 coloring of the faces, and we are interested in arrangements where one of the color classes, in our pictures it's a black one. The black color class is only triangles. And here you see some examples. So these animals exist, and actually there is a doubling technique which was used in some papers where they study the maximum number of triangles a pseudo-circle arrangement can have. And this doubling method yields, starting from a triangle saturated arrangement, it gives you another triangle saturated arrangement. And yeah, so the claim is that triangle saturated arrangements are three-colorable. And the proof is quite easy. So we define the white dual by just putting a vertex in each white face, and we connect them if the two faces touch at a vertex. And because all the faces of this new white dual graph correspond somehow to the black faces, and since all the black faces are triangles, all the faces of the white dual are triangles. And now we use a theorem of tight. Triangulations are rainbow three-edge colorable. So rainbow three-edge colorable means there's a three-edge coloring so that every triangle sees all three colors. And the proof of this statement is very easy. So we use the four-color theorem. We take a coloring with the binary vectors of length 2, and then for the edge we take the color which is the sum of the two vertices, and this is a tight coloring. And then if you have this edge coloring here, every edge is going through a vertex of our original arrangement graph, and you put the color there, and every triangle sees all three colors, and this is a valid three coloring. So it's a very simple proof based on this tight thing. Yeah, and then let me tell you about an observation which also comes from these triangle saturated arrangements. So if in such an arrangement you find a five-gon, and then you do this, you add another pseudocircle which is just enclosing this five-gon. We call it the corona implant. It started in when the corona things came up, and the picture is a bit like the virus. Now we can argue that doing this, the chromatic number is increasing to 4. And yeah, so let's do some easy countings. The graph is 4 regular. So the number of edges is 2 times number of vertices. You have a certain number of black triangles and a single black five-gon. Because we started with everything was triangles, and now in the interior of this new cycle, somehow the colors changed, and you have triangles and 1 five-gon. So from this we get that the number of edges is 3 times triangles plus 5. Every edge is incident to a unique black face. So the number of triangles is an odd number. And now let's look at an independent set size alpha, and we count pairs where the vertex is in the independent set and the face is incident. Since every vertex is incident to 2 black faces, we have x is equal to 2 alpha, On the other hand, every triangle is only incident to at most one of the guys from the independent set, and the pentagon to at most two. So we get the bound delta plus 2 on the number of pairs here. And now the x is equal to 2 alpha and upper bounded by delta plus 2. This is this thing. And now we use again that the number of triangles is odd, and we can make the inequality stricter. We gain a 1 here in the inequality. And now we multiply by 3. 6 alpha is less equal 3 delta plus 2, but 3 delta plus 5 is the number of edges, and the number of edges is equal to 2v. So we have a 2v minus 2, and then you divide and you see that the alpha is less than number of vertices over 3. So the size of the independent set is not big enough to allow for circularability. Yeah, and we conjecture that this construction that I showed you yields an infinite number of 4 critical arrangement graphs. So from what we saw, we are quite close. It's not yeah, they're just merely 4 colorable. And one to support the conjecture, there's a Köster example of a 4 regular 4 critical arrangement graph. This is a few years ago. It was, and this example can be obtained with this construction. So Köster had a different construction which he calls crowning, and from this he built 4 critical graphs. But yeah, we think that our construction has the same kind of properties. Okay, and now let's look at fractional colorings. So fractional colorings of arrangement graphs. If we have an intersecting arrangement, then we can find an n-2 coloring, meaning that every vertex is going to have a collection of n-2 colors with 3n colors in total. And yeah, we have 3n colors. What are we going to do? If we remove a pseudocircle, then we can color the interior with 3 colors, and we can color the exterior with the same 3 colors. So we take n collections of 3 colors each, and each pseudocircle is colored in with each of the palettes except for the 2 which correspond to the 2 pseudocircles which intersect in this vertex. So it's n-2. And this shows that the fractional chromatic number of the arrangement graph is at most 3n over n-2. So it is 3 plus something which is little o1. And yeah, and in this class of intersection of graphs of intersecting pseudocircle arrangements, we also find examples where the chromatic number is 4 and the fractional chromatic number is 3. So this is the very same example that we saw before, where we studied that the chromatic number is 4. And now here you have a B coloring with B equals 2 and 6 colors. So the fractional chromatic number is at most 3, but of course, because it is a triangle, it is 3. And so this is something that was new, that you can find these two values for chromatic number and fractional chromatic number of planar graphs. Yeah, and you can also grow the examples, get bigger examples with these properties, with a crowning construction like this. Yeah, so let me get to the end and just recall some of the conjectures that I mentioned in the course of the talk. So the first one was that the Grünbaum conjecture 2n-4 still holds for circle arrangements when they are simple, intersecting, and diagon free. And then if we give up on the diagon free, then the number of triangles of the pseudocircles should be at least n-1. And then the Diagons in the same class, the number of Diagons is at most 2n-2. And then some coloring things. If you have great pseudocircles and the arrangement is simple, then the chromatic number should be 3. If you have sufficiently many, then again, and some properties, and again the chromatic number should be 3, and even the strengthening to colorings of projective line arrangements with at least 7 pseudolines in this case. Yeah, so I stop here. Thank you for the attention.
Okay, thank you very much, Stefan, for this very nice talk and nice slides that you prepared. Are there any questions from the audience? Maybe unmute yourself.
So I have one. So you talked extensively about this family of graphs arising from pseudocircle arrangements. I wonder if there could be an alternative characterization of this class of planar graphs. Say a planar graph coincides with the graph of a pseudocircle arrangement, if and only if it satisfies the following properties. Have you thought about such a characterization?
Well, I mean, certainly you can find some statements which are more or less obvious, if say in terms of edge colorings or so, that you ask for edge coloring so that in each degree 4 vertex goes through, and these colors form simple cycles or something of that. But I don't know of anything interesting. Yeah, it's
Maybe also an algorithmic question about deciding whether a graph is from this class.
Yes, yeah, that's a nice question.
I mean, this is easy. You can do just that. So you trace these these that you go through, and
if it's simple.
and the connectivity is typically you talk about 3 connected graphs. So also the even if the graph is not given with an embedding, then still you get the unique embedding and you're done.
Okay, are there other questions? I have some also. So for example, what can you say about the number of digons and triangles in great circle arrangement graphs?
Well, if you have a great circle arrangement graph, then you can pick one of the great circles and look at the others, and they will form a Euclidean arrangement. And together with this equator, you can think of it as a projective arrangement. So it tells you that you have n triangles on each side. You have at least 2 n triangles. And regarding Diagons, you don't have Diagons in great circle.
Right.
You only have group.
And are there any non-trivial statements you can say about larger phases? Like you mainly talked about digons and triangles. Is there anything non-trivial, I don't know, about the distribution, or I don't know, of 4 phases and 5 phases, or how they relate somehow?
It's a good question, and it's certainly worth looking at it.
I don't know if you have many of those, then you have to have few of those or something like that.
So I can say that for Euclidean arrangements, people have been studying things in this direction, and there's, for example, if you don't have bounded phases of lengths more than 5, and the structure of the arrangement is very simple.
Okay, are there other questions from the audience? It doesn't seem so. So thanks very much, Stefan, for the nice presentation.
Thank you.
Thanks everyone for joining.